Okay, so it is 3:19 and we are doing problem types we hate in preparation for the test tomorrow. So the big one that came up for everybody was force of tension with multiple wires and where it's moving. So we're going to start off with one that's just hanging. We've got an 57 kilogram object hanging. Cables are making a 28-degree angle with the ceiling, and we want to know the force of tension. Since it's not moving, sum of forces on each axis equals 0. If you have a hard time remembering the MA thing, might I suggest that you start these like this, reminding yourself that it's still equal to MA, but A just happens to be 0. And that may be useful for you. So I'll go ahead and replace that. Okay. So we've got sum of forces on the X, and what are they? Well, they're force of tension on the X1 plus force of tension, or I should say, I guess, minus force of tension on the X2, because they're opposing one another. So all that tells us is that force of tension 1 times, what would that be? If we move this little line up here, it would be cosine theta equals ft2 cosine theta, which just tells us that ft1 and ft2 are equal. It's just sort of a proof, and we don't always need it, but it's useful to know how to do that, because that's what proves to you mathematically, algebraically, that those two forces of tension are equal. So now, having done the little proof, I'm just going to shrink all this, because the real action here, of course, is on the y-axis, because that's where we have force of gravity just sort of mentally grip, as it were. So it's equal to the MA, but the acceleration is 0. Therefore, that's 0. And it's also equal to the forces up minus all the forces down. Well, what forces up do we have? We have a force of tension Y on each of these. They're, of course, in the same line, though they're sort of imaginary, but I've drawn them separately just so we can see them. So we have force of tension Y1 plus force of tension Y2, and that is all, of course, minus the force of gravity. So I'm going to sort of recopy this, noting now that since that's 0, ft1, and the y-axis would be sine theta, plus ft2 sine theta, together equal the force of gravity. Okay. Well, because we proved up here that ft1 and ft2 are equal, and we know that theta1 and theta2 are equal, we can just say 2 ft1 sine theta, and we know that Fg really is equal to mass times gravity. So at this point, it's pretty simple to solve for Ft. So Ft equals mg2 sine theta. So what is the force of tension on this object? So we're taking the same object, 57 kilogram person, box, mastiff, I don't care. And now we're going to accelerate it upwards on these two cables at 1.6 meters per second. We still want to know force of tension. So we can still do that little handy proof on the x-axis. So sum of forces on the x equals ma, but is there any acceleration left to right? No. So if that's 0, then that's 0. And we have ft1x minus ft2x equaling 0. So ft1, and of course the x-axis is going to be cosine theta, equals ft2 cosine theta. So we've just done our little sort of geometric proof that those are in fact equal, and then we'll set that aside in case we need to refer back to it. The y-axis is where all the action is. And sum of forces on the y is going to equal ma, but in this case, ma is not 0. We have an acceleration. So sum of forces on the y is also equal to all the forces up, ft y1 plus ft y2 minus the only force down, gravity. So I'm going to rewrite that ma equals fty1 plus fty2 minus, and I'm going to go ahead and sub in my mg. So obviously we can flip the mg over to the other axis, ma plus mg. Now I know that ft1 and 2 are equal, and I know I could have written this as ft sine theta. So I could just now say 2 ft sine theta. Well, again, that makes it pretty easy to solve. Whoops, I don't want to move my ft over there. 2 sine theta, if I divide both sides by 2 sine theta, I have ma plus mg over 2 sine theta equals ft. So what do we get? Okay, so I'm getting 692.6617 on and on and on. A lot of you are too. We have 2 sig figs, so 690 newtons we'll have to do. An interesting problem then is to look at, how many times greater is the force of tension when you're being accelerated 1.6 meters per second upward compared to the force of tension when you're not. Is it 1.6 times as great? No, it's not. Okay. Do you feel okay with force of tension, multiple wires, moving stuff, or do we need to do more of them? Do we want to revisit any more of them? And that's where sum of forces will save your life. So yeah, that's a good point. On anything where you've got a force of tension and you have an upward acceleration, if you do that sum of forces, you quickly see, oh, well, there's a force of gravity down. And when I see people make the mistake of forgetting gravity, it's usually because they didn't do a sum of forces, and so they didn't account for all the forces on the object. Anything else? Should we move on from here, or?
Are the forces of tension
If the angles on the cable are, yes. If the angles on the cable are not, then no.
If the angles were not the same, you'd be solving for 2 different forces.
You'd be solving for 2 different forces of tension. If you know the angles, that's not hard.
Yeah.
And if you know a relationship between the angles, like a ratio, the tension in this cable is 3 times the tension in that cable. That said, like the Mastiff problem or whatever we were hanging from the ceiling with the 2 unequal angles, like that's a homework problem, where you weren't given the angles and you had to work back to the angles. That's craziness. I wouldn't do that on a test. It's too much. And that's really more testing your sort of analytical geometry and not your ability to do the physics that I want to assess you on. Yeah. So, I won't say that having 2 different angles is totally off the table, but I wouldn't do something like that. And remember that on my tests, always you get at least 1 skip in each category. So, other questions before we move on to just sum of forces? Okay, we can come back if we need to. Let's do a sum of forces net force problem. As I'm starting to draw this thing for you, I'm realizing that The bigger problem for you is usually actually drawing it from the description, isn't it? Once you've got the free body diagram, it's a piece of cake. So it's drawing the free body diagram from the verbal description. So let me actually make this harder. Straight up net force, box pulled by 3 ropes. 1 rope at 28 degrees north of east exerts 721 newtons of force. Rope 2 at 41 degrees south of west exerts 675 newtons of force. And number 3, rope 3 at 15 degrees north of west exerts 569. We want to know what the net force on the box is. Okay, now do you have something like that? I didn't draw my vector lines to great scale, obviously. My 569 should be shorter, my 721 should be longer. But you should come up with something that looks approximately like that, did you? Wunderbar. So, now, for actually getting your net force. Well, everything has to be broken down into an x and a y axis. So all of these have components on the x and the y. And I tend to draw them in for myself because I find that it prevents really stupid mistakes down the road. So I'm also going to list these for myself. So for 1, let's see, it would be, what, force 1 on the x equals force 1 cosine theta. Force 1 on the y equals force 1 sine theta. Okay. That was easy. But having that note to myself will help. And having that visual representation. Somebody said to me this week, oh, I don't even look at my free body diagram. I just draw it because you told me I have to. Well, that doesn't actually help. So you should actually be using it, and especially if if you've ever screwed up a which is the sine, which is the cosine, the free body will save your life. So force 2 on the x equals force 2 cosine theta. Oh, I guess I did these all where all the x's are cosines. That was nice. Force 2 on the y equals force 2 sine theta. I'll set that aside. And then for force 3x, force 3 cosine theta. Oh yeah, I guess I'm assuming that the thetas are color-coded for me because I'm a visual learner, but you're right, I should do that. Hold on, let me finish writing this and I'll do that. Yep, cosine 1, 1, cosine 2, 2, cosine 3, 3. Yeah, that would be helpful. Okay, so now that I've got those set up, I need to write something. And this goes all the way back to doing non-perpendicular vectors, if you can believe that, from chapter 3. So my resultant, my net force, which is my resultant, is equal to the square root of my sum of forces on the x squared plus my sum of forces on the y squared. And if I write that the minute I've finished my free body, what that reminds me of is, oh, I gotta find my sum of forces on the x and y. So it's a handy reminder. So if I look at my sum of forces on the x, well, what do I have? If I call this my positive direction and this is my negative direction, which you don't have to do, you can just do magnitudes, it's up to you. I would then have f1x, which is that direction, minus f2x, because it's that direction, minus f3x, because it's also that direction. So my sum of forces on the x would be f1 cosine theta 1 minus f2 cosine theta 2 minus f3 cosine theta 3, because those, and I'm still putting in my stupid little arrows over those so I don't screw up. So let's go ahead and real quickly, I'm not going to write the numbers in here because I'm limited on space. Go ahead and you write it down and we're going to compute it. So let's find the sum of forces on the x. Okay, so I've got my sum of forces on the x. I drew that little arrow over it as a reminder to myself because for the folks who are struggling with, how do I visualize that net force, having those arrows can be really helpful. So let's shrink that and write my sum of forces on the y. Well, I've got, and again, I'm going to call this positive, this negative, just imposing Rene Descartes' little system on my world here. F1 on the y, which is up. I'm going to group my positives and negatives together. So plus F3 on the y, and that's the only reason I'm doing those out of order, minus F2 on the y, which is south. Okay, so I've got north, north, south. And I'm going to write those in with the expressions that I built. Sum of forces y. So F1 times sine theta plus F3 times sine theta minus F2 times sine theta. And again, I'm not going to write them in because my space is limited. It gets hard to read. But I'm going to go ahead and compute. You do the same. Okay, so I get 42.917 in pocket change, and it's north. So it's up on our little picture, Cartesian positive. So now what do I do? Well, now because I have those arrows and I know that these vectors mean something in the actual real world, and I'm going to color code these. I apologize in advance for the high percentage of colorblind individuals I have in this class. Much higher than usual, I will say. I am literally going to take that 422 and I'm going to draw it here. And I'm literally going to take that 42 and I'm going to draw it here. And I'll go over those in black for anyone who's not as interested in the color as I am. Now I am going to do my resultant, my net force. That shows me that my net force is here. So that's where I know where my heading on my net force is. Because I took my sum of forces on the x and the y and I drew myself a little stinking triangle. And so that's what, you can all do this part. That's easy. You can been doing Pythagoras since you were in 8th grade. But what's harder for a lot of people, or when do they do it? You've been doing it since earlier than that? Pythagoras? Okay. Okay, actually, yeah, I don't really remember not knowing Pythagoras. But anyway, we've been doing Pythagoras a long time, people. You can do that in your sleep. Finding the heading, visualizing what this means in the real world is the harder part. So now, once you find the magnitude of your resultants, you have an opposite side. You have a 42.9 blah, 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 and you have an adjacent side, 422.43 blah, blah, blah. And so you can take the tangent, inverse tangent function of 42.9 blah, blah, blah over 422 point blah, 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 and you can get theta. Oops, that should be in the other spot here. Does that help? It's a stinking bunch of accounting work. And you can't really shortcut these. Law of cosine does not work on these, correct? I don't think it does either.
I think it's too much more complicated than this.
Yeah, it probably is. It's just accounting. That's all it is. So it's keeping good track of stuff. If you want to sit down to your test with a pack of colored pencils, I'm fine with that. If you're a visual person and you need to color code it, I'd advise against using markers or highlighters or pens because, math and pen is never a good idea. But use colored pencils. Okay, now, let me ask you this. if this object has a mass of 35.6 kilograms, what's its acceleration? Okay, so we've got a net force of 424.61 newtons at a heading of, so second function, tangent, the 42 divided by the 422, heading of 5 degrees, 5.80 ... yes?
Yeah.
Pretty shallow angle. I mean, it's going, almost due east. Not quite, though. So what's the acceleration? So we know that F net equals ma, so F net divided by mass equals acceleration. We have the 424.6, etc., divided by 35.6. We get an acceleration of 11.927, etc., meters per second squared at 5.80 times, 5.80 north of west. Okay, you good with that? Are there other problem types we hate? Do you still hate these? Are there other things that you're thinking like, crap, this is what I screw up? What are the common mistakes? Other issues that you want to address? Do you want time to just look through all the homework? You've got all the homework back. I will have the friction labs back. I've got all the keys, and I just have to, it'll go fast. I'm going to do that fourth period. So if you want your friction lab before you leave tonight, and the ones that I've seen so far have all been pretty good. People have done all the sums of forces. I haven't found anybody who cheated on sums of forces and tried to do one generic one for each angle, and The whole point was to make you write them a bazillion times so that you would never again take for granted that Fn equals mg. Because before I talked about that so much, I had people who would actually turn in that whole lab writing Fn equals mg and figuring all their coefficients of friction wrong. Can you even imagine that? You look like I just, kicked a cat in front of you, because you would never do that. You know better. Okay, any other questions? I will leave you to pour through your own stuff. There are extra copies of probably most, if not all, the FIP quizzes here. So go for it. I'll put on the radio, the Redidio, in the 2 minutes we have left.